Okay, so obviously we need to do these notes because they matter. Yeah, I'm trying to make you groan even while making this video. Okay, so let's let's just take 2 seconds before we get into these notes and just take a look at the schedule again. You probably just watched the density worksheet 1 video, and the audio quality was really good on that. I'm being sarcastic, of course. I'm not quite sure what's going on with my microphone here. Apologize if it's a little scratchy or quiet or anything like that. Maybe you took Element Quiz 1 and now you're about to, or are currently watching the Matter notes, and you have homework tonight. Don't forget to do Matter Worksheet 1. Our lab next class is very dangerous. There's going to be fire and acid and all sorts of crazy things. But while we're talking about, the upcoming things, the matter notes that we're about to do have a lot of vocabulary in them. And if you flip to the page, it has all the vocabulary list. These terms, all of these terms, you need to know these terms before we go into the test. All right? You need to know every term up here. Some of these guys we just covered in density, so you're probably good on them, but we're about to add a whole lot to them. If you're not good at acquiring vocabulary, you need to make some sort of extra effort here. Like, how are you going to remember what malleability means? How are you going to remember what boiling point means or filtration means? You need to come up with some method for making sure that you learn these terms. For me in vocabulary, it was always about flashcards. Um, that way I forced myself to think about it a lot. I was a flashcard kid, just who I am. Luckily, however, most of these terms, if you grew up here in Loudoun County, you have been using in science since the 4th grade. A couple of them might be new, but most of them are first introduced in the 4th grade. So let's start at the notes. Flip pages. Yeah, yep, there we are. Okay, it's this page like 20, I don't know something. But matter. What is matter? Oh, we got some sort of alert. Matter is pretty much everything. Everything you can see, feel, or touch is made of matter. And we're going to spend a whole lot of the year talking about matter and how it's divided up into atoms. And atoms are the individual pieces of matter that we focus on. And then they can further be classified into elements. And so there are atoms, which are all the little Lego building blocks of our world. And then if you want to classify the Lego building blocks into different categories, we call those different categories elements. If it's a Lego brick with that's 3 by 2, a 6-piece one, that's got a name. If it's a 2 by 4, that's got a name. And every single type of atom has a different name or different classification, and those basic classifications are called elements. What the primary thing that determines what type of element it is the number of protons. I'm going to actually throw a line underneath that because I have the skills. The number of protons. This is so important that we call the number of protons the atomic number. Um, there are other parts of an atom that are important, but not as important as the number of protons. So if you tell me that you have an atom with 6 protons, I pick up a periodic table, I look across, and that is carbon. Yeah, carbon has 6 protons. If you instead say you have an atom with 2 protons, I look at the periodic table, atomic number 2 is helium. That's a very different element than carbon. And so each atom is divided into categories called elements, totally based on the number of protons. We're going to spend more time talking about protons, neutrons, and electrons in the next unit. But this one's just kind of like the basics. How do we divide matter? What happens when matter mixes? Things like that. So here we have a periodic table. There's also one in the front of the classroom. If you all look to the left, you'll see that big periodic table. Sometimes I have them around the room, elements all over the place, but each element has an atomic number. Here's iron, 26 protons. Ooh, carbon's number 6 is missing. That's very weird. What's up with that? Iodine, look, it's 53, so 53 protons. Chlorine has 17 protons. Every periodic table has this basic amount of information, the atomic number, and the symbol. You just took a quiz on the symbols, so you already know that we use symbols to represent the different elements of the planet. Um, some of the symbols are weird, like potassium. Potassium is not potassium everywhere you go. Sometimes they say calcium instead of potassium, but our word potassium comes from background where they used to find potassium in the ashes that were burned in a pot. So the ashes that were burned in a pot became potassium. Anyway, there's all these historic backgrounds behind each weird symbol you see up there. Some countries have slightly different names, but every country uses the same symbol because we're all chemists are underneath this one big organization called the International Union of Pure and Applied Chemistry, so that we have a common language. And the periodic table is that language. And you guys are going to learn how to use some of that this year also. Welcome to your foreign language class. Um, so the other thing we're going to talk about here is what happens when two atoms combine. It depends on the two types of atoms. So let's just draw a dividing line on this periodic table here, right here. This dividing line separates two very distinct sides. On this side of the dividing line, we have metals, and on the other side of the dividing line, we have non-metals. And how these two sides combine really changes their properties. And so there's going to be a couple different classifications you see here. But remember, as we talk about these things, any element that's on this side of that diagonal is a non-metal. Any element that's on this side is a metal. You could probably figure out this side's the metals because it's got iron on it, and it's got copper on it, and gold and silver. Um, but a lot of these other elements are kind of foreign to you, and you might not know bromine or you might not know osmium, but you can get a couple that kind of serve as your basis. So what is a molecule? A molecule is where two atoms bond, but those two atoms have to be nonmetals. So if you have two nonmetals bond, we call the bonded atoms a molecule. That might be the oxygen you're breathing in, or the nitrogen you're breathing in, or any one of a number of combinations. And molecules do something called covalent bonding. We're going to spend an entire chapter later in the year talking about covalent bonding. But all we're really gathering here is that if you have nonmetals combining together with other nonmetals, we call that a molecule. And there are a couple of special molecules that bond to themselves, where these 7 elements automatically bond to themselves. Anytime you have oxygen alone, it finds another oxygen and they buddy up. You have iodine alone, it finds another iodine and they buddy up, and they become two atoms stuck together. And we call these two atoms stuck together, well, look what we call them, two atoms, call them the diatomic elements, because these two atoms automatically bond with each other anytime they don't have other elements to bond to. So if you have a bottle of hydrogen, you have a bottle of H2. If you have a bucket full of chlorine, you have a bucket full of Cl2. They're often written in this order, HOFBRINCL, so that it can kind of be said like it's a word, Hofbrinkel. Um, it's a real common little acronym just to remember which 7 elements uh, kind of bond like this. Also, if you look at a periodic table again, these 7 elements almost form the number 7, except hydrogen's over here. Okay, so HOFBRINCL. There's 7 of them, and anytime you have one of those 7 elements alone, it automatically makes a molecule with its identical twin. All right, so molecules are nonmetals that have stuck together. What are compounds then? Compounds are different. Compounds are a metal and a nonmetal. I don't see that up there. Oh, there it is right there. So compounds are metals and nonmetals. All right. So sodium and chlorine. Sodium is a metal? Yeah, there's sodium right here. Sodium's a metal. Chlorine's on this side. It's a nonmetal. So that's a metal with a nonmetal. And they form what we call compounds when they come together. And again, this is the other type of bonding. You maybe remember ionic bonding from your 8th grade class, or maybe from earth science. In ionic bonding is where the elements are coming together and electrons are actually being stolen from one and shifted to the other. And we're going to spend a good deal of time talking about that process later in the year. But right now, we're just learning that anytime you have a metal and a nonmetal come together, they become an ionic compound. One other really unique thing here is that when they combine together and form a new compound, they become something completely different. So, for instance, salt. I'm pretty sure that everyone in the room has eaten salt, tasted salt, put salt on food. Delicious, right? When sodium and chlorine combine together to form salt, some magic happens. Electrons are transferred from the sodium to the chlorine, and every aspect of the sodium and chlorine becomes completely different. When you have just sodium and separated from just chlorine, when they are separated, they are toxic, dangerous, deadly substances. Sodium, when it hits water, catches on fire. If you put pure sodium into water, it catches on fire. If you put chlorine out there, chlorine is a toxic gas that will fill your lungs and choke you to death and kill you. But when you take the flammable sodium metal and the toxic green chlorine gas and you bond them together and they form salt, everything's different. Everything's different, and they're delicious. Um, and so the point of that is that once elements combine, their properties completely change. It's true with molecules as it is true with compounds. That simple combination changes everything about them. Solids, liquids, and gases. You've been hitting this forever. We're going to spend a whole chapter later in the year discussing the molecular side, the micro side, what happens, why are things solid, why are liquids, why are they gases. But for right now, simple definition, holds shape, holds volume, spreads out, fills the space. Make sure you know the 3 definitions. Um, these pictures here, brought to you by NASA, might all have the same mass, but you can tell how the mass is spread out differently. In the solid, the mass is tight and held together in a strong form, fixed shape. The liquid, it is spread out to fill the bottom of that cube. And then gas, it is spread out to fill the entire cube. But what's important about the gas is you can really see the space in between, whereas the solids and the liquids, it's harder to see the space in between because they're so close together. Okay, physical changes and chemical changes. So these things are pretty easy. All right, kind of lost my train of thought. Had to walk away for a second, but I'm back. You probably But only just a pause occurred. So I was just about to talk about physical and chemical properties and changes. These two terms can often be confused. So a physical property, something that can be observed, as you can tell by this scratchy red line there, without the substance becoming a different substance, meaning it might look different, but it's still the same thing. And I usually focus on the can you reverse it. Pretty sure I just spelled that wrong. Um, let's go through these things up here. Density. You can observe the mass. You can observe the volume. Is it still a chunk of metal? Yes, it is. That's a physical property. Boiling point. You boil the water, it becomes steam. Is it still water? Is it still H2O? It is still H2O, and to prove it, you could cool it off and condense it right back to H2O. Same thing with melting. You got an ice cube, you warm it up, it's liquid. You cool it off, it's a solid. So that's where I apply the reversible aspect. Things that are easily reversible are physical properties. Ductility, this is not the ability to turn into a duck, no matter what you've heard. It's actually the ability to turn something into wires. And metals can often be smashed and squeezed and hammered into different shapes. So we warm them up with a little energy, and then they become soft. We spread them out, and if we could put them into wires, then they are ductile. So ductility is really about making wires. Well, malleability is similar. It's about shaping things. It's about shaping things and reshaping them again and again and again. Metals are definitely malleable and they're often ductile. Where non-metals are not malleable. They are not ductile. There's that dividing line again. Metals on one side, non-metals on the other. Oftentimes something is good for a metal, not good for a non-metal. Conductivity. We're really talking about heat or electricity here. Um, right off the page. Uh, some metals are great at conducting heat, but not electricity, and vice versa. Non-metals are usually neither good at heat or electricity. Um, but all of these things can be observed and still maintain the substance. You could put a piece of metal over top of a fire and see how quickly it gets hot. You could try to run electricity through a metal, see if it'll conduct electricity. That's still a piece of metal afterwards. And then the easy things for physical properties is I looked at this metal, it is shiny. I looked at this metal, it is orange. I looked at this metal and it conducts electricity. Those are the easy things. You just look at them and you know what it is. Chemical properties, though, chemical properties are really talking about making a new compound or any sort of or molecule. Moleculed? I don't know what to be. So we're making something new. You light the paper on fire. It reacts with oxygen. You get ashes. You have smoke. You have fire. Um, now you have something new. Something that's different than the original. Maybe you put some lithium out on the counter, and after a while, the lithium changes from silver to, I don't know, let's just say white. That's exciting because it's reacting with oxygen. And then you have a new compound. You have lithium oxide. So it's changing as it reacts with the air. And that's one of the most key words you're going to see with chemical properties. You see the word reacts. Um, so if it reacts with something, It is definitely a chemical property or chemical reaction. Um, what does corrosive mean? Corrosive means that that substance is going to react with other things and break it apart. Acids tend to be described as corrosive because they'll break compounds down into smaller pieces and react with them. Explosive. Explosive means that it is moving really rapidly from a small volume to a high volume, and that explosive change of volume usually causes a ton of damage. Most of you just kind of have a visual image of what explosive is, but if you think about it, you have this small object that a reaction occurs inside, and that small object expands ridiculously fast and throws things away, right? Pushes things away. So an explosion is this rapid conversion of energy and matter from a dense zone to a very high volume, low dense zone. Bam, and it goes. And then flammability. Not everything catches on fire. Well, not everything catches on fire at low temperatures. So if I put a piece of metal in the fire here at school, it's not a hot enough fire to burn it. And there are different temperatures for fire. You guys don't really get to experience fire much. Most of our observations are usually through touch, and hopefully you're not touching fire, but there are very different temperatures for fires, depending on the color of the flame, depending on what's being burned. Um, and some substances don't burn until they reach 2 or 3,000 degrees Celsius. So, but whether it can burn or not, that's a chemical property. Because in order to figure out, you try to light it on fire, and as you light it on fire and it burns, it's now making a new substance. It's reacting with oxygen to make something new. And things react with oxygen so often, we often say that they are oxidized. Let's add that also in there, oxidized. That entire same conversation about physical properties and chemical properties, you could replace it with chemical changes and physical changes. Um, The melting point is a physical property. Watching something melt is a physical change. So watching it melt or boil, those are physical changes. Watching them occur. Knowing the temperature at which it's going to occur is a physical property. Um, Chemical changes, again, just like before, there's a reaction occurring and you have a new substance afterwards. Let's play a game here and try to guess what it is. So let me pause as I think of some examples and type them up here. All right, so I threw down 5 things over here. I typed them up, and we're just going to try to figure out which side they would go on. Let's start with condensation. So condensation, is that a chemical or is it physical? Let's see. So you have a gas. Condensation is that gas becoming a liquid, but it's still the same substance. It's still whatever molecule it was. If it's water as a gas or water as a liquid, still water, so it's a physical change. All right. So it's still the same substance. That's a physical change. Battery leaking. Ooh, battery leaking. Feels chemical, but when a battery leaks, get all that white crystals or yellow crystals coming out. There must be something else going on there. There must be some sort of reaction occurring between chemicals and the metal. That is actually a chemical change. It's eating its way through the metal, and it's trash now. Um, and that's actually some acid that's inside that's breaking through the metal finally. So battery leaking is a chemical change, and remember that one of the tests is it reversible? Can you undo condensation? Yes. Can you undo battery leaking? Only if you're a wizard. If you're a wizard, that's fantastic, but that's still a chemical change. Food rotting. Which one is it? Nope, it's actually chemical. Food rotting is a chemical change. Again, apply the blah, 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 reversible rule. Um, your potato is sitting on the counter. It is been ignored by everyone in your family for 4 weeks, and it just looks disgusting. You can't turn that disgusting pile back into a potato because the compounds inside have been slowly breaking apart and uh, going through that process of rotting, and it's not a reversible process. It's a chemicals are changing inside the potato. It's too late. You should have eaten it when you first cooked it. Acetone vaporizing. First of all, let's say, what is acetone? Acetone is found in nail polish remover, and we have a lot of it here at school that we use for various things throughout the year. Um, so acetone is a nail polish remover, and as a lot of the people in the class can tell you, nail polish remover gives off a smell that is the smell of the liquid turning into a gas or vaporizing. So if it's just going from liquid to gas, it would be physical change. And then cutting paper. Cutting paper, the reversible rule doesn't quite work with cutting paper because it's not like you can magically stick the two pieces of paper back together. But I do have this question. Is it still paper? Yes, it is still paper, whether it's in one piece or two pieces. So it is not changing chemically, it's still paper. So it's a physical change only. So a lot of your homework on worksheet one is going to be just identifying physical or chemical, physical or chemical. And what I've done here is I have kind of given little explanations for each thing. And so you might struggle with some because there's not enough explanation. We'll have a good conversation about those. Pure versus mixture. This is hard for a lot of kids because you don't encounter a lot of pure substances in your daily life. Almost everything you encounter is a mixture. But pure substances are one element or one molecule or one compound. Uh, the table salt you have at your house is almost a pure substance. It's mostly sodium chloride, but it's usually also got sodium iodide in it. And since it's got another compound in it, it's technically a mixture. Ugh. Um, but if there's only one compound, one molecule, or one element, then it's a pure substance. So let's make that clear again. If you have aluminum, where's my cursor go? There we go. If you have a bar of aluminum, you have a pure substance. If you have aluminum oxide, you also have a pure substance. It's one compound again and again and again, versus this is one element again and again and again. If you only have one compound in the bottle or one element in the bottle, you have a pure substance. It's got one set of properties or inside that bottle. Where with a mixture, though, you might have your aluminum and, I don't know, gold. You got aluminum and gold together, you have a mixture. You got two different things, two different elements that are not bonded together. So maybe you've got little beads of gold and beads of aluminum in the same bottle. They're not actually bonded, they're just like little BBs in there. So you have a mixture. And then mixtures get classified in two different ways. Are they mixed evenly or unevenly? So if it's the same everywhere, it's a homogeneous mixture. If it's not the same everywhere, it's a heterogeneous mixture. Um, and so let's just come up with two quick. So salt water and salad dressing. There we go. Those are two simple ones. Um, Salt water, the salt dissolves into the water and it almost appears to disappear. It's really just spread out so uh, small you can't see it anymore. and so it's mixed in to the entire solution. Salad dressing, you end up having layers of things, and you shake it up and you pour it real fast because if you wait even a second, it starts to separate back out because it's got very different properties and the mixture is not an even mixture. Alloys are a type of mixture. They're when metals are bonded together. When they're bonded together, they can be separated again. If you melt the metal down, they'll separate out based off of their masses and their densities. And you don't have to memorize these, but let's just take a look. If you put copper and tin together, you make brass. You put copper and zinc together. Oh, I said that wrong. It clearly says bronze, doesn't it? Copper and tin, you make bronze. Copper and zinc, you make brass. And they have very different properties. Brass is shiny, it's harder. Bronze is easier to shape, but it is not as pretty and it doesn't last as long. It tends to be a little bit more brittle. That's because the zinc and copper atoms are just about the same size on the periodic table, but copper and tin are not the same size. But again, I'm going too far here. Iron and carbon. You mix iron with a little bit of carbon, you make steel. You mix iron, carbon, and chromium together, get stainless steel. So that the chromium changes the properties just slightly. But you can separate all this stuff out. You can just melt it down and then separate the metals right back again, which is kind of what we do in the recycling process with a lot of metals. We just melt them down and reform them. Now we're talking about separating those mixtures. Distillation, this is the most common method used for separating liquids. Let's focus on the fact that that says liquids right there. All right. Liquid mixture. So this is two liquids in here, and then the heat source, which is this adorable little Bunsen burner, is heating the liquids, and one of them is going to boil. Not both of them, one of them. If you have water in here, water boils at 100, and a lot of alcohols boil at around 75. So you could heat the water and the alcohol together. The water would stay in here for the most part. The alcohol would boil and then get forced down this tube. And this tube is pretty cool. It's actually surrounded with another glass tube that's cold. Because that other glass tube is cold, the alcohol is going to condense and then drip out onto the other side. You would not actually want to use a Bunsen burner if you were boiling alcohol, though. Alcohols are extremely flammable. This is a good way to get an explosion on your hands, and we don't want the rapid expansion of, in this case. Um, when like I do this, separating oil into its various components is also distillation. It's just distillation on a huge scale, where they take the black tar and they boil it, and it gets separated out based off of its boiling point. Um, Filtration, this is gonna be done in our lab. We're gonna be filtering some solids out. Um, but the key there again in the focus is that this is for separating solids and liquids, where distillation was for separating liquids and liquids. Chromatography, we separate things. It's called chromatography because it's usually separated. We get to see the colors. Chroma is color. And it's good for, well, we're going to do a lab on it where you can see what it's good for. Here's a quick little flow chart about is it a mixture, is it a pure substance, can it be broken down further, are things mixed together well, and there we go. I think we're done with the notes. Hope you guys are having a good day, and get to work on worksheet 1. Don't forget, dangerous lab next class, bring the right clothes.